Yeah, everybody, Mr. Covey here, and this is a video going over what we went over in class on Monday, Tuesday, which is finding the connection between functions and their inverses in terms of derivatives. So there's a connection between a function, its derivative, and its inverse's derivative. It's a little bit complicated. It doesn't have a name. At Lake Forest High School, we call it buddy points. Okay, that's not the official name. We call it buddy points, but it's not. Anyway, real quick, I'm going to go through this kind of quickly. Let's recap real quick what a function and its inverse are, what's the connection between them. If you were going to describe a function and its inverse, you'd say they are opposite functions, but I don't like the word opposite, so what I usually think about is one function undoes the other. Okay? So if two functions are inverses, they undo each other. The opposite of x squared is square root of x. There's some domain issues there, but the idea is, what's the opposite of x squared? Square root of x. Okay. Numerically, this is the important one. Pay attention. If you have a point 2, 4 on a function, then the point 4, 2 is on its inverse. Okay. I don't think we emphasize that a lot in some of our algebra classes. Really important. Graphically, they're symmetrical over the line y equals x. Okay, so if you draw the line y equals x, they're symmetrical over that line. And last thing, how do you actually find an inverse? Well, we'll go over that in a second. But you might remember flip the x and the y, solve for the y. Okay. So what is an inverse function? An inverse and a function, they undo each other, so when you do composition of them, they cancel each other out. If you do f inverse of f of x, you get out x. That is the definition of a function and its inverse. They cancel each other out. You do them both, nothing happens. How do you find inverse? You switch the x and the y and you solve for y. That's the thing I think you guys remember most about inverses. Just a quick vocab here that's important. Monotonic means always increasing or decreasing. It's going to come up in the ideas today. What is 1 to 1? It means for each x, there is only one y. It's similar, well, it's not similar. It's different than what it means to be a function. For a function, each x only has one y. For 1 to 1, each x, there's exactly only one y, and vice versa. Meaning, for each y, there's only one x. Not all functions are 1 to 1. 1 to 1 really means it passes the horizontal line test. Okay. So all functions pass the vertical line test. 1 to 1 functions also pass the horizontal line test. Functions and their inverses are effective over the line y equals x. And then buddy points. Okay. So that's this idea. This is what I want you to focus on. The idea of a buddy point is if you know a point on a function, then if you flip the coordinates, you get a point on the inverse. Okay, this is an important idea. If you have a point on a function and you flip the coordinates, that flipped point will be on the inverse function. Okay? We call these 2 points, well, they're different points, but we call them buddy points. They're friends with each other. They're buddies. Okay? Okay. So the reason we talk about 1 to 1 is because it ensures that the inverse will be a function. Okay, so if your original function doesn't pass the horizontal line test, then the inverse won't pass the vertical line test. So if you want your function's inverse to also be a function, then it has to be 1 to 1. Okay. How do you know if a function's 1 to 1? It passes the horizontal line test, or you can think about it as being monotonic. If it's either increasing or decreasing, if you think about a function that's always increasing, it's going to pass the horizontal line test. Okay? There's not a horizontal line that's going to hit it more than once. If you have a function that's increasing and then decreasing, it's going to fail the horizontal line test. It is not going to be 1 to 1, and its inverse will not be a function. Just a couple of other kind of random things. If a function is continuous, its inverse is also continuous. This one's a little weird. If a function is increasing, then its inverse is also increasing. A lot of times people think that it flip-flops. No, think about it visually. We'll see a picture in a second. But if a function's increasing or decreasing, then its inverse is doing the same. Okay. Lastly, if a function is differentiable at a point, then its inverse is differentiable at the buddy point. So last one's a weird thing. We'll come back to that in a second. Okay. Okay. I hope you look at this and you're like, yeah, I remember how to find an inverse, Mr. Covey. Okay. Here's your function. We're trying to find the inverse function. We write it with a y instead of an x. We flip the x and the y. We do algebra to get the y by itself, and you write it with that fancy inverse notation. This function undoes the original function. If you did composition of them, they would cancel each other out. What I mean by that is if you did this, let's just do it real quick. F of f inverse of x, you just get out x. Watch. Take f, plug in f inverse into it, do algebra, you just get out x. Okay? They are inverses of each other. Okay, so here's just another example of finding an inverse of a function. Here's the function. How do you find the inverse? Place the f of x with the y, flip the x and y, get the y by itself. Okay. And it's nice to write with that function notation. Okay, so here's the important idea, the calculus idea. We'll get to it in 1 second, but what I want you to note before we get there is that this algebraic process involves flipping the x and the y. So in inverses, x's and y's flip. What that means is domains and ranges flip. What that means is points themselves flip. Okay? So there's a lot of flipping around going on when you look at a function and its inverse, and there's something related to that that happens with functions, derivatives, and their inverses derivatives. Okay? Here's what it is. It's a little bit confusing. I'm just going to make up. So first off, red and blue are inverses. They're symmetrical over y equals x. Whatever that red function is, it looks like a cube root graph. The blue one looks like a cubed graph. They're inverses of each other. Okay? Here's the calculus idea. If you take a point on the red function, let's call the red function f of x. We'll call the blue function f inverse of x. If you take a point on the red function, let's say, I'm just going to make it up, that point's 0.2, 0.8. And if you look at what you think the slope at that point is, the derivative at that point, I would estimate it's like, I don't know, what, a fifth? I'm going to write in calculus notation. F prime of 0.2 appears to be a fifth. Okay? So I would write that here. If you look at the inverse, because 0.2, 0.8 is on f of x, 0.8, 0.2 is on the inverse. Okay, so the point with the coordinates flipped around is on the inverse. And if you look at the slope at that point, it's certainly not like the same. No. It's the reciprocal of what the slope is at 0.2. Okay, so if you look at the slope at 0.8, here's where the notation gets a little confusing. It's not 1/5, it's 5/1. Okay, so the idea is the derivative of the inverse is the reciprocal of the derivative of the original. I'll say that again. The derivative of the inverse is the reciprocal of the derivative of the original at the buddy point. I cannot emphasize that again. At the buddy point. These 2 points are not the same points. They're buddy points. Okay? So knowing something about the derivative of f at point 2, point 8 tells you something about the derivative of f inverse at point 8, point 2. It doesn't tell you about the derivative of the inverse at point 2. It tells you about the derivative of the inverse at the buddy point. Those are not the same point. They're buddy points. Knowing the derivative of the original at a point tells you something about the derivative of the inverse at the buddy point. The reason that we made up this buddy point thing, and I didn't make it up, it was long before my time, back when I was a young boy. Someone at Lake Forest made it up. Is because it's confusing that those 2 points aren't the same point. They're buddy points. Okay. Okay. Here's it in fancy notation. F and G are inverses. What does that mean? Well, it means when you do composition, they cancel each other out, you just get out x. Then here's the excuse me. Here's the derivation, but here's the idea. Then the derivative of g is the reciprocal of the derivative of f, not at x, at the y value of g. It's because it's at the buddy point. Okay, so why is this formula even useful? Well, it's cool because if you know an original function, you can find out things about the derivative of the inverse without actually having to find the inverse function. Okay, that's kind of the nice thing about it. Okay, so you know something about a function, you can know something about the derivative of its inverse. Okay, the derivatives of the here's the key phrase here. Read this. The derivative of the inverse function at a point is the reciprocal of the derivative of the function at the corresponding point. We call this corresponding point the buddy point. But again, the key focus here is that it's not at the same point, it's at a corresponding point. Here's it summarized one more time. The slope of the line tangent to the inverse at x equals b is the reciprocal of the slope of f at x equals a. Okay, at a different x value, at a buddy point. Okay, you'll see it once we do this together. Okay, here's a little bit more fancy stuff here. Yeah, that's just what we're saying. Note that if the slope of your original is 0, then when you do the reciprocal of it, you're going to get undefined, so that can mess it up. But besides that, here is how we would summarize it. Slopes of inverses at buddy points are reciprocals of each other. Okay. Hey, there's me and my buddy Mrs. Fry. Note this picture was taken last year, pre-COVID stuff. Okay, so here's that picture that I try and draw before for you guys. Take like a minute to look at this picture. Okay, so here's the calculus part. If you look at whatever the derivative is at this point, then the derivative at this point will be the reciprocal of it. Notice these are not the same points, they're buddy points. This one's a f of a, this one's f of a. Okay, let's just do some problems. I think it'll make more sense. Okay, let's just do this problem. So we have a function, f of x. And they're asking us to find the slope of the derivative at an x value of -3/4 without taking the derivative of the inverse. Normally, they wouldn't even tell us the inverse is derivative. But this is a good example where the inverse is a little messier, and so taking this function, finding the inverse, and then doing the derivative of the inverse is kind of a process. So instead, we're going to use this new idea. Okay, this is how it works, right? First thing you got to do is draw a burrito. No, you're thinking, what is, I don't know how to spell burrito. That's not how you spell Come on, Mr. Covey. You gotta draw a burrito. Why a burrito? Because it's a buddy burrito. You gotta draw a buddy burrito. Kind of looks like a cylinder, it's a buddy burrito. What you put in the buddy burrito is this. I should draw it a little bigger. And these buddies are in the way. Let me draw it down. What you put in your buddy burrito is your original function and the inverse. And you keep track of what we're trying to do here. So we're trying to find the slope of the inverse at negative 3/4. So we're looking for an x value of negative 3/4 on the inverse. Well, its buddy point will have a y value of negative 3/4 on the original, because they're buddy points, okay? So what we need to do is complete the buddy point, okay? We know the x-coordinate of the buddy point on the inverse and the y-coordinate of the buddy point on the original. We need to find the x-coordinate on the original, which will be the y-coordinate on the inverse. We need to fulfill the buddy point. We need to complete the buddy point. I'm just going to do that with the original function. So I'm going to say, hey, if I have a y value of negative 3/4 on f of x, let me find the x value that goes with that. So I'm going to add the 1 over. I'm going to divide by 2. Just do an algebra here. I'm going to cube root both sides. I'm going to get a half. Oops. Okay. So what that tells me is an x value of 1/2 on the original gives me a y value of negative 3/4. So x value of negative 3/4 on the inverse gives out a y value of 1/2. So now I have these two buddy points. This is on the original, this is on the inverse. I'm going to try and find the derivative or the slope of the inverse at negative 3/4 by looking at the slope of the original function at 1/2 at the buddy point. Okay, so I'm going to look at f prime and find f prime of 1/2. Here's f prime. F prime of 1/2 is 3/2. And so since f prime of 1/2 is 3/2, the derivative of the slope at the buddy point is 2. Okay. Things about the derivative of f at this point tell me things about the derivative of the inverse at this point, namely the reciprocals of each other. So since f prime at this point is 3/2, f prime of the derivative at this point is 2/3 at the buddy point. This is the buddy point. Let's do another one. You'll get a better feel for it. Other comment. There's a little bit of notational confusion here because when you write the inverse and you write the derivative, they kind of look similar. So we usually avoid writing the derivative of the inverse like that. A lot of times you'll see it written something like the derivative of the inverse. You know, something like that. Okay, that's all that done out. Not as nice as our burrito. I really like the burrito. But you can pause and look at that if you want like a fancy math notation. Here's some other notation that's good. Okay, next one. Hey, there's me, my buddy, Mrs. Or sorry, Miss Rupnick. Cool. So we're trying to find the slope of the inverse at 3 using the fact that the original function is this. We're not going to actually find the inverse function. This is an example of finding the inverse. If this is actually super messy / I don't know how to do it. So we're just going to use this relationship, this buddy points idea. So I'm going to draw my buddy burrito. Mrs. Lemke does not like the buddy burrito because she doesn't like burrito. She's more of a quesadilla lady. I don't know why. Anyway, for the buddy burrito, I have my original and my inverse. Because I'm looking for an x value of 3 on the inverse, that will correspond to a y value of 3 on the original. What I need to do is complete the buddy point. Okay? In other words, I need to figure out what x value on the original gives out a y value of 3. I am going to write this equation, and I'm going to realize that I don't know how to solve that, so I'm going to use my calculator to solve that. I'm going to type this into y1, this into y2, figure out where they intersect. I figured out they intersect at 2, So I've completed the buddy point. 2, 3 is the point on the original, and 3, 2 is the corresponding point on the inverse. I'm now going to find the derivative of f. I'm going to find the value of the derivative at 2, because that's my buddy point. That's why you write out the burrito, so you make sure that you don't plug in the wrong stuff. Do my math. Get out 4. Because the derivative of f at 2 is 1/4, the derivative of the inverse at 3 is 1/4. I'll say that again because I think I said it wrong. Because the derivative of f at 2 is 4, the derivative of the inverse at the buddy point is 1/4. Okay? I'm just going to emphasize again, the main mistake people make is they forget the buddy point idea. They say, oh, because the derivative of f at 2 is 4, the derivative of the inverse at 2 is 1/4. And I say, no, you forgot the buddy point. The other mistake people make, since we're talking about mistakes, is they say this. I'm sorry, let me write this out. They say, hey, the derivative of a function is the reciprocal of the derivative of the inverse. Or they more often the other way around, and they say, hey, if you want to know the derivative of the inverse, you do 1 over the derivative of the original. And I say, no, because that's ignoring the buddy point idea. Okay? That's completely ignoring the buddy point idea. The derivative of the inverse of this is not 1 over 3x squared, 3/4x squared plus 1. No. It's only at the buddy points. This is a point-by-point system. Related to that, how do you find the derivative of the inverse of this function? You find the inverse and find the derivative. The only time we can really use this buddy points idea is if we actually are trying to find the derivative of the inverse at a particular point. Okay? There's the long fancy explanation if you want to look at it. Okay. I'm going to do one more with you and then I'll let you guys try a couple. Okay. There's me and my buddy, Mr. Freeman. Here's our original function. We're trying to find the derivative of g at 6 and g and f are inverses. Draw your buddy burrito. Because I'm looking for an x value of 6 on the inverse that corresponds to a y value of 6 on the original. Let me complete my buddy point using algebra. So a y value of 6 on f. Nope, that happens at math, x equals 2. So that's the x value for f and the y value for g. I'm going to do f prime of x. I'm going to get 3x squared. I'm going to evaluate the derivative at 2, not at 6. Everyone looks at this and tries to do it at 2 because of the buddy point idea. Don't forget to look at your buddy point. I'm going to get 12. So then g prime of 6 is the reciprocal of that. I hope you're feeling better about this once you kind of get the feel for it. It's a lot of details to keep track of, but that's kind of the tricky part. There's the problem done again. There's a visual. The slope of f at 2, 6 is 12. So the slope of g at 6, 2 is 1/12. At the buddy point is the reciprocal. Okay. All right, I'm just going to give you 2 more problems to do. This one says find the equation of the tangent line to the inverse at the given point. If you're confused about whether this point is on the original or the inverse, look at it. Is this point on this? No. 10 cubed plus 7 times 10 plus 2 is not 1. This is the point on the inverse. Okay, so here's the point on the inverse. I want you to write the equation of the tangent line to this inverse function at this point. Okay, you need to find f. Oh no, sorry, that's bad. You need to find derivative of f. Should do your buddy points thing. You should get 1/10 as your slope. You have your point. Here is the equation in point slope. One more for you guys here. Here's f of x. This is a point on the inverse. Find the equation of the tangent line at this point on the inverse using this buddy point idea. Okay? Equation of the tangent line. Go for it. All right, that's what you should have gotten as your answer. And that concludes this video. Thanks for